a presentation looking at processing in a very sophisticated way RNA-seq data, terminating with an iLinks analysis. And then we've had sort of a summary and a nice overview of how iLinks works in a very granular way, including thinking about some of the really important technical things like Dr. Schiefer brought up, I know this in the audience. And now we're going to shift a little bit towards more the drug discovery end of things. And Dr. Meller alluded to our next speaker. This is not Dr. Jim Reigle, this is Jim Reigle. He's currently a graduate student at Cincinnati Children's in the bioinformatics program. He is shared with Dr. Meller and I at the moment, which is great. Jim went to Wheaton College for undergraduate work. He did a master's, I think, in physical chemistry at Northwestern, and is part of the proteomics pod in my laboratory with Dr. Funk. And of course, Sig2 lead is his baby. So I'm not going to say anything more about him. Let you tell us all about it. Jim, take it away.
Thanks, Tom. All right. Thank you for the nice introduction. I'm going to tell you a little bit about Sig2 lead. This is an application that we developed in YARC and lab, and also in coordination with Rob. I want to preface it with saying it was a team effort. It's not been one person that's developed this, and a lot of the fun that we've had in developing it was just the fact that it was such a cooperative group of people. So the title of my talk today is Sig2 lead, Integration of Omics Signatures and Chemical Similarity for Improved Structure-Activity Relationship Analysis. So essentially, I know some of these concepts have already been touched on, so I'm not going to spend a lot of time on. One of the principal concepts of Sig2 lead is CMAP, in the sense where we find concordances between various signatures and profiles. And it's also built upon the links database, and YARC's obviously just went in detail about that. Those are two of the principal concepts of the application. And you've seen this slide already, but essentially what we're just as a refresher, we're looking at basically a set of signatures and how they correspond and how their correlations, whether they're up or down or positive or negative. So CMAP has been used in pharmacogenomics already. It's done for novel phenotypic relationships. We've looked at drug mechanisms of action. It can be used for drug repurposing. Also experimenting with combinations of drugs and doing experimental validation. And you've seen this as well. This is the LINKS Consortium, 6 generation centers throughout the U.S. And Mario Medvedevich is one of the key people at the University of Cincinnati where we work. So the idea is essentially, and Yard mentioned this, that there's around 40,000 small molecule signatures in links, about a little over 40,000. There's about 7,000 gene knockdowns. So essentially what Sig2 lead does is you can input a gene, it'll find the gene knockdown signature, and then it'll query that against the small molecule library. So essentially the idea is that if you know that if you're interested in a particular gene target, and you say you put that in, you can it'll immediately find for you a set of small molecules that have the same cellular effect. So if you know you knock this target down, the cell has this expression profile. In conjunction with that, if you treat the cell with one of these small molecules, the same effect occurs. So that's kind of a major principle of Sig2 lead, and I'll get into that. And this is more of a concept of the application. In the demo section, I'll get more into the actual details. So what is Sig2 lead? It's essentially a bioinformatic tool. It integrates pharmacogenomics and cheminformatics to enhance in silico identification of putative inhibitors of a specific target. Essentially, the idea is if a gene target, gene is knocked down, the small molecules that you find that are concordant with that are most likely pathway inhibitors. Because if you're assuming you're knocking out a gene, you're affecting a pathway. And that if you treat that same small molecule that's concordant with that, then you're understanding that that small molecule is probably interacting somewhere in that pathway. You don't necessarily know the exact target. It might not be a direct interaction, but you know that in some way that they're influencing the same effect. We take it a step further in sig-to-lead though. So what I've talked about so far in terms of the concordance is just the first part. We also extend it and bring it into cheminformatics when we talk about chemical similarity. So it's not just that we're looking at the concordance between small molecules and the gene knockdown. We're also looking for chemical similarity between these linked compounds that we come up with and other compounds that a user may provide. And that's something that in the demo I'm going to explain a little bit more in detail. That one of the nice features is that you can come up with your own compounds. You might have compounds that you're interested in seeing what they do in a certain cell. You can add those to sig-to-lead. If they're not immediately in links and come up with the gene target, they might actually correspond in terms of similarity with one of those links compounds. And then they could possibly be an analog of the same type. You don't know for sure, but it might have the same mechanism of action as one of the links molecules. We also take it a step further than that, and once we know those small molecules, we can actually use Stitch, which Samchai in my lab, in Yarik's lab, developed, that basically maps those to pathways. So it takes the genes, it takes the small molecules, and it constructs a network pathway that gives you insight. Now that's built on, you have to be a little careful about direct interactions with that. It's built on a database and also text mining in literature. So it's basically the known interactions. So just to go over kind of pictorially, the general concept is we have, essentially in the upper left there, we have the gene knockdown. We query that via iLinks through sig-to-lead against the links data, the small molecule database, and we get a set of concordant molecules in the links database with that gene knockdown. Now I want to make one thing clear. I have another thing here. We have virtual screening. This is not built into sig-to-lead directly, so it's not part of our application. The idea, though, is that, especially like in drug discovery, that people are doing virtual screening, and you can use sig-to-lead in tandem with that. So someone could be look at a set of candidates, do screening, and then see how they come out when running sig-to-lead, see if they cluster with any of the links compounds, and you can infer mechanism of action and so forth with that. So there's virtual screening, which is external. We map similarity-wise to those links compounds that are concordant to the knockdown, and you get a set of clusters. And those clusters, for instance, like we have one that's from virtual screening and 3 from links, it's possible that they have the same mechanism of action, so it can give you information. And I believe Yarik showed this, but this is more the first concept in terms of connectivity mapping. So essentially that we're looking at the gene knockdown signature, and then we're looking at the small molecule inhibitor signature, and we're looking at the concordance between those two. So exactly in terms of trying to break this down to why you might be interested in using it, sig-to-lead can be used by itself to give you, for a variety of routes, for basic science in terms of trying to understand mechanism of action, etc. But it's really designed to use with other techniques like virtual screening. So one thing that we've looked at is in terms of looking at true positives and false positives, with looking at how virtual screening is enhanced by using sig-to-lead. So the question is, how would you know? How can we increase the true positive of virtual screening method via sig-to-lead? Essentially, you can use it enriches that, so you can find it. And we have data for that. That our results show that there's an enrichment in true positives in combination with sig-to-lead, in combination with virtual screening. So in terms of the concept of chemical similarity, the second concept, the first is the connectivity map and concordance. Essentially what we do, and I don't want to belabor this point too much, but essentially what we do is take each small molecule, and you would do this with, and you can provide, if you have your own compounds that you would like to look at, you can actually put those into sig to lead, and you can put them in the SMILES, which is a short code for the molecule, or you can actually import them as an SDF, which is actually a 3D, that's a text file that has the 3D coordinates of all the atoms. And what sig to lead does is it converts it to a binary vector. And essentially, so this is a way to represent any molecule that you want, pretty much, in terms of a one-dimensional string of bits. And that's the way that we can use it computationally. I mean, you can't work with a 3D molecule very easily. But if you flatten it this way, you can look at correlations and similarities between those vectors. And that's one of the key principles of sig to lead. And essentially what we do in terms of measuring similarity, we actually use what's called the Tanimoto coefficient. I don't know if people are familiar with that. It's essentially what's also called the Jacquard distance. It's looking at the intersection of two vectors related to the union of them. So essentially what you do is you match, basically, if we have, so number one is, say, one small molecule, and number two is another small molecule. You can see that if there's ones, we basically give it that's in the intersection. If there's two zeros, it's in the intersection. If it's a 0 and a 1, it's not. So they're different and so forth. And with that, we can get a score, and you can see how similar those two molecules are. So what is an example workflow? I'm not going to go into great detail on this because we have I think a good example to show you the details in the demo section. But I tried it with the ADRB2, which is the adrenergic receptor expressed in the brain. And let me just show you just a few key features. The screen essentially is the implementation that currently is written in is an R-Shiny app. So it requires R and R Studio, and I'll show you how to download that in the demo. Essentially what we have is a search. Up here to the upper left, we have a search tab where you can input the gene. We have links compounds, and these are the concordant compounds that come from there. We have a heat map, a combined score, a multi-dimensional scaling plot, similar compounds, global stitch, and I'll go into all these details later. But essentially what we have here is, for a given gene knockdown, so we put in ADRB2, and what the queries iLinking gives you a set of small molecules across down here that are concordant with that knockdown. So it gives you a set of molecules that could be inhibitors, just like the gene knockdown. So that's for the links compound, and then what we do is we generate a heat map. So it takes the gene knockdown, it queries that, it gets the small molecules from links, and then you can actually add your own compounds too, which are shown in magenta there in the heat map. We cluster that, and you can see groups of clusters, and you can see where your added compounds cluster in relation to the links compounds. So you can see in this lower left that there's a strong group of magenta, which are the user provided compounds. You can see there's a strong group of that with the links compounds. And the measure we're using this is the Tanimoto similarity. So all these molecules have been converted to a vector. And then we can rank them. We calculate. So we basically get a concordance. This is the concordance which for the links compound, and then we find the similarity between the user-provided compounds, which I'm calling my compounds here, and the links compound, which is the LSM ID is here. And you get a similarity. We're experimenting with a new score. This is not developed. It's not benchmarked yet, so we're not going to talk about this too much. But we're looking at methods of how we can combine concordance and similarity to get a combined metric that gives an overall score. But that's still in development. One of the nice features we do too is with the user provided and the added compounds, we get the multidimensional scaling plot, which actually basically allows you to visualize a high dimensional data matrix in 2D. And so essentially what we have is the circles or the pies are a cluster from the heat map I showed you. And if it's in the orangish color, reddish color, they're links compounds. If it's in the green color, it's the added compounds. the longer the distance between different pies, you are saying that they're less similar, so they're farther apart in the heat map. And then you can say when they're mixed together with links and my compounds, you're saying at that threshold that those compounds cluster together. So you can find where your added compounds cluster with your links compounds. And in this case, I just took one out. This is a set of user-provided compounds that I ran with the ADRB2, and it contains a set of, these are the set that's actually of compounds that are in there. This is not specifically for ADRB2, but this is work that Samchai's worked really, in my lab's worked really hard on. This is essentially an output for local stitch. Essentially, this is when it has a set of genes and a set of compounds. It queries the available knowledge in the literature, and it constructs a network. The nodes are either, the circles are genes, the kind of rectangles are small molecules, and then when there's a line between them, there's an edge, and you're saying there's a known experimental validation that there's an interaction between those two. And then something that's recently been added, and I had a nice example of this. It's kind of zoomed in for the demo, but this is also something Samchai did. This is the global stitch. So essentially, when you do stitch, you're basically extracting a cluster, the local stitch. You're extracting one of these clusters. So you can say, for instance, the big one on the right there, number 2. You can take that cluster, put it into stitch, and it'll give you a network. But the other thing you can do is you can take all the clusters, and that's what global stitch does. So it essentially takes all the clusters from an NDS plot and then plots a network together. And so you get one massive network, and then you can zoom in and try to find the interactions you're interested in. How much time do I have? Okay. In terms of benchmarking, just to run over this, first of all, one thing we did, and we're in the process of doing really extensive benchmarking for the paper, but we essentially just took a set EGFR gene. We ran sig-to-lead. We ran it through sig-to-lead with 16 known inhibitors of FDA-approved known inhibitors of EGFR, and we wanted to see if sig-to-lead retrieved them either in the first part in terms of in links, or in the second part via chemical similarity, and it found all of them. So essentially, they retrieved the first 9, this set of 9 compounds here. When we ran EGFR, they were actually in links, so we actually were already in there. And then the remaining 7, the ones up here, we found in the clusters with links compounds, so that they were retrieved as well. We also looked at sig-to-lead as an alternative to virtual screening. So I don't know, Yarek mentioned this a little bit. Essentially, virtual screening is a method which looks at the spatial orientation of a ligand with a protein, and sees whether it's energetically favorable for it to interact. And it's not as time consuming as the wet lab methods to use for that, but it's time consuming. And so what we're looking at with sig-to-lead is that we can essentially speed that process up. So we look at, instead of doing virtual screening to find candidate drugs, could we have what's our true positive rates on a library that we know the answers to for sig-to-lead, and we found that this is what's called an ROC curve, and essentially you want the higher to the left and to the top it is, the better it is. That shows that your true positive to your false positive rate is better. And essentially, for various thresholds that we cut at, you can see that the upper line here is sig-to-lead by itself, that the true positive rate was much higher than the random. And then the other thing we're looking at is sig-to-lead in conjunction with docking. So if you want to do them in tandem, we found it's not quite as dramatic, but we did find that this MTI is the virtual screening tool, and you can see that we had an increase when we did sig to lead with the top 500 from virtual screening and the top 100 versus MTI alone in black. So this is the black is just in virtual screening by themselves. So you can see that we enrich for true positives using sig to lead. So essentially what we're thinking is time-wise, and we're in the process, like Yark said, the application is not fully developed, it's still evolving. But we're making it faster and faster, and some of the times here it's saying, I think that Alex made this slide, actually said that it took like 5 minutes to run sig to lead on for roughly a 2,000 compound library, which takes about 45 minutes for docking. So essentially, the idea is that you can enrich with using this method in a much faster way. And we've been working in the last probably month to 2 months on really making it faster and have added a lot of features. So we're not even there yet. So just to summarize, what added value does sig to lead offer? It gives us connectivity between a target knockdown and chemical inhibition signatures. It extends structure-activity relationship by combining connectivity with chemical similarity, and it allows for enrichment in conjunction with docking. And I'd like to point out this little graphic was made by Beirut's in our lab. He's pretty proud of it. We actually had T-shirts made with it. So, and you've seen this picture already. This is the Meller lab where this was developed, and I think Yark already went over everybody in the picture, but I'm happy to answer your questions.
EGFR inhibitor.
Well, now let's use the mic.
So our viewers, remote viewers. Okay, with the known EGFR inhibitor, we found 7 linked compound analogs.
Not yet 9, I think.
So have you tested them for the efficacy against EGFR?
In terms of wet lab, you mean, or
Inhibition of EGFR? Activity?
we haven't done any wet lab. We've done in the sense that we know that the pathways are the same pathways are affected because the target knockdown and the chemical small molecule signature were concordant.
The other thing you answered me at the end with the sig to lead with docking, that maybe better way of getting the link analogs. Make it much better, let's say you have 2 compounds in the visual screening by docking, and then you pull more link analogs later using structural similarities.
Exactly.
But subsequent docking would validate more of the link analogs better.
We're experimenting with different orientations and so forth and ordering whether to do which one first. The idea is that it can be used in conjunction. In terms of wet lab, Alex, that was one of the key developers of this, did actually a lot of the actual experiments in the lab to test these, and you're talking like a year or 2 to do 50 compounds or something takes a long time. So this is the idea is that we use this tool to choose smarter candidates and more informed candidates so that you're not spending as much time and money in the lab. That's the idea.
So thank you, James. We're going to keep going.